All right, so where we left off is when we're on the inside, bam, there's the parallel one right through the focal point. There's the one that would be coming from the focal point, but from that direction, goes out that way. That's a diverging one. And so what happens is we follow the light backwards here. So if you're looking on this side over here, you'd actually see an image back behind the lens, but that's what a magnifying glass does. It makes things look larger than they really are, makes it easier to see things. There's nothing really there. There's no light focusing back over here. It's called a virtual image. Okay? But it's actually, once you get in, the object is inside the focal length, it's diverging light here. Okay? So you can't make an image. So that's the convex lens. Let's go, or the converging lens. Let's go the other direction, the other kind of lens. Okay? All right, concave. So kind of the same story-ish, but different. Light coming in parallel. Well, remember, it diverges. It doesn't bend towards the focal, it bends away from the focal point. But what it bends away from is backwards line of sight to the focal point over here. So technically this is a negative right over here. This is the negative. Reason this is a negative because this would be the focal point over here of the lens. This is the positive side for the light because this is the light coming in. This would be the positive side for the image would be. But since we're not really using the positive focal length over here where the light is, we're using where the light isn't, that's a negative focal length back over here. And so keeping that in mind when we get to the math portion. Alrighty? So it bends away, but how do you know where it bends away? Well, it bends away from the focal point, but the negative focal point. Alrighty, so how about light coming in? Light coming in at an angle is coming in towards the focal point. Well, that bends in parallel. So we're using light coming towards the positive focal length over here. It doesn't actually go through the positive, it gets bent parallel. Okay, so light coming in at that angle towards that would be bent parallel straight out. And of course, just like our other kind of lens, the converging lens, light going right through the middle, sure, there's some bending in there, but as it comes out, it gets bent and comes out the same direction, going through the middle. Same way up here. So those are the three rays that we can use to figure out exactly where the image would be, what kind of image it is. Is it erect? Is it inverted? Is it real or not real? Okay? Alrighty, I think we might only be doing one of these, because the nice thing is they're all the same. It's not that exciting, but they're all the same. So there's the object. So let's go ahead and draw one straight through. Remember what happens straight through? It's diverging, so what has to happen? It has to bend. Oh, okay, I'm clicking. I'll click again. There it is. It bends away, not towards the focal, away from the focal, but towards that negative over here. So what's another one we can draw in there? Right to the middle. Let's see which one they choose. Oh, they did the middle one. Hallelujah. Now, there is another one they could choose. What would be the other one you could choose? The other one you could choose, and they're not going to do this, I'm pretty sure, so I'm going to go ahead and show you this. Whoops, did I turn my pen off? Okay. The other one is, they did the right through the middle one. The other one that they could have done is the one going towards the focal point. I'm terrible at my aim here. I should be using my pen. So I'm going right towards the focal point, everybody, and boom. Remember what happens when light is going towards the focal point? Scoop, there it is. It goes right in the middle. So it's still diverging. They're all diverging away from each other. And where's the image? Well, look at what happens backwards, guys. Bing. We're doing the whole backwards thing to find out where the image is. And let me get rid of my pen. I don't think I need that anymore. And there it is. So, whoops, I lied about the pen. So to understand what's going on here, think of your eyeball. I'm going to make a massive eyeball over here. And Once again, it's all bloodshot and everything. But the reason I make it so massive, so you can see, it doesn't matter if it's massive or small, we're still taking in light from all different directions. And it bends it back into the light bulb and forms an image over here. We'll get to some slides on that in a little bit, how the eye acts as a converging lens. But the point is, the eyeball doesn't see things in the curvy nature. The eyeball sees this light coming in a straight line this way. The eyeball sees a light coming in a straight line that way. The eyeball sees a light coming from a straight line that way, so they all converge right over there. So, a couple things. It's upright, and it's smaller. It's going to happen for every single concave. Because it's diverging, it will never make the object larger. The magnification will always be less than 1. Not only that, you can't focus the light to make a real image because it's diverging. Because it's diverging, you cannot make a real image. You can't put a piece of paper anywhere over here and form a real image. You need an eyeball that can refocus the image, or another lens that could refocus the image somewhere else. And the eyeball is another lens that could work. But you cannot put a sheet of paper or a screen behind, anywhere behind this, on this side of where the eyeball is, and get an image because the light is diverging. But that eyeball can see an image, and it's teeny, and it's behind the lens there. And it turns out that's what happens for every single image with the concave lens. It can be larger than that, it can be smaller than that, but it's always going to be a virtual image. There's actually no light right there, no image being formed. It's a virtual image. It's always going to be upright, and it's always going to be smaller than the object. Doesn't matter where this object is, it's always going to be like that, okay, in every case. So that's the nice thing about the diverging lens. It's all the same. Doesn't matter if you're outside 2F, inside 2F, or wherever you are, it's always going to work out the same. So that's going to be it for that one, I bet. Yep. So let's get into the math. I know how much you guys love the math. So now to find out where images would be located mathematically, well, if you know the focal point, 1 over the focal point equals 1 over the image and 1 over the distance. Now, in your math, it's going to call this on your math, it's your AP sheet, it's going to call this an S for position. It's going to call this an S for the position of the image. It's all the same math. Okay, they're using an S instead of a D. Okay, that's just what the highfalutin collegians do. They think they're better than everybody else. But here's the thing about it. For diverging, it's pretty much straightforward. Okay? I'm sorry, for converging, it's straightforward. Diverging is tricky because remember, we're using the opposite focal length. It's a negative. So the focal length will be negative for the diverging lens, which is that concave that we're talking about. And whenever you have an image that's on the opposite side of where the light is, that's going to be a negative image, which can happen with a magnifying glass when you're inside the focal length. When you have a non-real image, a virtual image that's magnified, it looks like it's on the other side where there's actually, that's not where the light is focusing. That's going to make for a negative image over there. Object's always going to be positive, guys. Always. There could be an exception with that. Well, no, the object's always going to be positive. I was going to say, what if you have a 2-lens system? We're going to leave it at that. So the image is going to be positive. If it's a real image, you can focus the light on something. It's going to be negative if you have a virtual image. And if it's virtual, it's going to be erect or upright. If it's real, it's going to be inverted for a single lens. And the focal length for the convex lenses or diverging lens, it's going to use the positive. You're going to use a negative focal length for the diverging or the concave lens. All right, let's get into some math. General rule. I think we just talked about this, didn't we? That's the lenses and mirrors, yeah. So that's positive for a real image and negative for the virtual. Okay, I think we just talked about that. Hallelujah. All right. Oh, a sample problem. Here we go, guys. This is converging. Are you excited? All righty. I know I am. There's old Toots. Oh, they ruining it for us. We should have tried to draw the ray stuff and figured out where this thing's going to be and if it's going to be larger and all that other stuff. All righty. Well, let's go ahead and practice this stuff. I guess we'll use the horn as the top. Okay, light coming in parallel, guys. What happens when light comes in parallel? Through the focal point. There's the loud friggin' cat. He thinks he's coming in. And it goes that direction. And then we've got light coming through the focal point. I should be using my pen, but well, I'm not. And boop, got it. Kind of, sort of, boo, and it goes out parallel. Okay. And there's a third one you can draw. You don't have to draw two, but I like to. And it goes boo right through the middle and doesn't bend. And there you go. Hey, so there it is. You notice it's a little bigger because we're in between the F and the 2F. So it's going to be a magnification greater than 1. It's going to be a negative magnification because it's inverted. And it is real because you can focus. You can put a card right there because look, we're focusing light to a point. Alrighty. So how do we do all the math on that? Alrighty. So what is the focal length of the lens? Okay, so it's going to be 1 over f equals distance or object distance. It doesn't matter which one you do first. And there you go. So 1 over the f equals an f equals 1 over the object. The object is, where the heck is the object? In front. So that's 24 American feet. And the image is 35 behind. Since the light is actually over there on the other side, and it's supposed to be, this is the positive for the image. If the image is over here, the image is not supposed to be over there because that's not where the light is. That would be a negative for the image. But since it's over here where it's supposed to be, it's a positive. So that's 1 over 35. All right, guys, you got to do a common denominator. Good luck with that. I'm going to use my calculator. It's much easier. All right, so 1 divided by 24 plus 1 divided by 35. Boom, 0.070. So that is 1 over f equals 0.070. So f equals 1 over 0.070. So 1 divided by 0.07, I'm not putting a 0, 14. So the focal length, guys, is 14 feet. 14.3 if you want to be more specific. Now, how do you find the height of that thing? Well, define the magnification first, guys. Oh, did we already see the magnification? We may have forgotten to talk about that. The magnification is the height of the image over the height of the object, or you do the image negative of the image positive of the object. Yeah, I don't know the height thing there. If I know the magnification, I can do that. So I'm going to do the S's first. Okay. So the image distance was negative 30. Well, because it's negative. So it's a negative 35. That just means 4. So 24 divided by 35. Oops. I did it backwards. 35 divided by 24 is 1.46. So the magnification is 1.46, and that equals the height over the actual object height, which is 4 feet. So to find the image, it's 1.446 times 4 and 5.8. Okay, so the image is going to be 5.8 feet high. Okay, and I'm getting right under the time for the old YouTube. Won't they be happy? There's my 14.2 or my 3. I did some rounding. And there's my 5.8. Oops. The negative just means on the height that it's inverted. Okay, so I didn't carry my negative through. Whoops, it's a negative magnification, meaning it's inverted. So technically it's a negative height, not because it's going down necessarily, but it's just inverted. Alrighty guys.